Okay. So our plan for today is to finish, or you know, I don't know if we'll finish. Keep working on the section on curve sketching. Before we do that, are there any questions? Oh, my elbow's like on the keyboard. Okay. Good. Okay, well, hearing none, we'll go ahead and get started. Hey, like everybody's talking about schools closing down, and there's a bunch of colleges that have closed their campuses for a bit. Where are you guys at? Any,
We have been given lights to light them.
Oh, okay, well, that's good. Yeah.
Yeah, that's not really fun.
Oh, you know what? Okay, sorry, hold on one second. My, for some reason, the touch screen on my tablet is on, so it's responding to... I want to just turn that off. Okay. All right, that should be better. All right, so the last time we got to start on this section, and we talked about how we could use the derivative to help us figure out when a function is increasing or decreasing, and when we get a relative maximum or relative minimum, and that the sign chart, we can make a handy sign chart that'll kind of help organize all that information. When we do this, like when we use this sign chart, and for example, like when we look here in the sign chart and we say, oh, well, the derivative goes from positive to 0 to negative, so that means we must have a relative maximum. We call that the first derivative test for maxima and minima. Just looking for a change in sign. And it's important to note that the sign actually has to change. It's possible to have a 0 derivative, but the sign doesn't change. Like it could go from negative to 0 to negative, or positive to 0 to positive, and that doesn't actually correspond to a maximum or minimum. So let's do another example. We want to find maxima and minima for this function, 3x to the 5th minus 5x cubed. So if I'm looking for maxima or minima, I'm going to use the derivative. That's my first step. So let's find y prime. It's a nice power rule derivative. Polynomials are always nice and easy. So we get 15x to the 4th minus 15x squared. So we found the derivative, but it's not enough just to get the derivative. If we're going to make a sign chart, we have to have it in a factored form. So we could factor out a 15x squared. And when we do that, we've got x minus 1 remaining factor, x squared minus 1 remaining factor, and then we want to factor as far as we can. So x squared minus 1, that's a difference of squares. The sign chart is only good, it's only useful, only does its job when I can make a row for each factor, not a row for each term. So it's really important that I've got it written as a product of its factors. So we have our first derivative. Next, we find those critical values. Critical values are where the derivative is 0. Where do we get a 0 derivative?
X equals 1 and equals 1, X equals 0.
Yeah. Yep. Great. So I want those critical values. I've got the factors and the critical values, which means now I can make my sign chart. I list the factors along, to make rows along the vertical axis. So I've got a row for 15x squared. I've got a row for x plus 1. I've got a row for x minus 1. And at the end, I've got a row for the product. which I'm just going to call y prime, right? Like the multiply them all together, that is our derivative. And along the horizontal axis here that's the real number line. So I'm going to just mark down those critical values in order. So -1, 0, and 1. Now we just fill in each row. The 15x squared is 0 when x is 0, but it's positive everywhere else because it's a square. X plus 1, that's 0 and -1. And if I plug in something less than -1, like if I put in a -10 or something, it'll be negative. And if I plug in something greater than -1, like if I plug in 0, it'll be a positive. And then we get similar behavior for the x minus 1 term, except that it's 0 at +1. And it's negative to the left, positive to the right. So the derivative itself is 0 at each of these critical values. We already knew that. That's how we figured out what values to put along the horizontal axis. But now we're going to fill in the signs for each interval. So for these values less than -1, is y prime positive or negative? Positive, yeah. And how about between -1 and 0? Negative. Between 0 and 1? Negative. And greater than 1? Positive. Great. Now we have everything we need to answer the question. We just wanted, they didn't ask us to find where is it increasing or decreasing, though we could. We just were looking for relative maxima and minima. So where do we have a maximum? Can you say that louder? Negative infinity to -1 is where it is increasing, but where we have a max is going to be a single point. So at -1. And so we've got basically half the answer. We know the max occurs at when x is -1, but we got to finish the job and get that y coordinate. So when x is -1, we have -3 plus 5, so y is equal to 2. Where do we have a minimum?
One.
When x is 1. So again, x is 1 gives us a minimum because it's decreasing heading into that. It levels off because the derivative is 0, and then it's increasing heading out. Similarly, when at -1, it was increasing heading into that value. It levels off because the derivative is 0, and then it's decreasing heading out. So this is at 1, and I think if you plug in 1 to the function, you'll get y equals -2. You get 3 minus 5. What's happening at x equals 0? Yeah, like it's decreasing heading into that value, then it levels off, then it continues to decrease. So maybe like at that instant, at that singular instant, it's neither increasing nor decreasing because the derivative is 0. But it doesn't change, right? It's not changing direction. So this is neither max nor min. And, you know, like it might look something like if it's decreasing heading in to it and then keeps decreasing, like that could look something like this, right? There's an example of what a curve might look like when you have a critical value and it's not a max or a min. Questions on that example? Okay. So we can use the first derivative to tell us whether something's increasing or decreasing. But it's important to note that it doesn't really tell us how a function is increasing. Like if you look at these two curves here, those functions are both increasing as x increases, but they're doing so quite differently. And the difference in the way those two graphs are increasing can be described by using its concavity. We would say that the graph on the left here is concave up, and the graph on the right is concave down. And similarly, you know, a function could be decreasing differently. So there you could be decreasing in a concave up manner, and decreasing in a concave up manner might look like this, right? Decreasing in a concave down manner might look like that. So we are going to look at how we can describe the concavity. What do we look at to figure out how something is increasing or decreasing? And on the next page, we can figure out whether something is concave up or concave down. If we look at this concave up shape on the left, you can see that there's a few tangent lines, segments that have been drawn. So look at what's happening to the slopes of these tangent lines. Here's a slope that's a little bit negative, then the slope is positive, then the slope is more positive, steeper. What is happening to the first derivative? So if these tangent slopes start out negative, they become positive, they increase more, they become more positive. This first derivative, f prime, is increasing, right, as x moves from left to right. If f prime is increasing, what can you tell me about the second derivative? So the second derivative is the derivative of f prime, right? And if f prime is increasing, what has to be true about its derivative?
Decrease?
Nope. If a function is increasing, what do we know about its derivative? This is a question we literally answered like a few minutes ago and a bunch of times yesterday. Like, I know you know the answer to this question. We're thinking about it in a different context right now because we're talking about the second derivative. But just think of a function. A function is increasing. How do I know when a function is increasing?
Positive.
Yeah, its derivative would be positive. So if f prime is increasing, then its derivative, which is f double prime, is positive. And that tells us that when a curve is concave up, then f double prime, the second derivative of that function, will be positive. Similarly, over here on the right side, we've got this curve that's concave down. We could sort of see it in action by looking at these tangent slopes, but the derivative f prime is decreasing, and that means that its derivative has to be negative, right? An f prime is a function in its own right. So if it is decreasing, then its derivative has to be negative. Now this gives us a couple of things, right? So it gives us a way to tell whether a function is concave up or concave down by looking at the second derivative. if I want to find out about concavity of a function, I will look at the second derivative and figure out whether it's concave up or concave down in the same way that I use the first derivative to figure out if a function is increasing or decreasing. I can make a sign chart, just see where f double prime is positive or negative. It also gives us another way to determine whether or not a critical value is a maximum or a minimum. So I'm going to do this up here in the top margin. Here's a maximum, right? And here's a minimum. At the maximum, that's a concave down shape. So if it's at a maximum, if it's concave down, that means that f double prime is negative. At a minimum, this is a concave up shape, f double prime is positive. So an alternative way to determine, like if you found critical values, an alternative way to figure out if your function is, or that if that value is a maximum or a minimum, is to just plug the critical value into the second derivative and see if you get a positive or a negative. You know, if it's concave up at a critical value, it's got to be a minimum. If it's concave down at a critical value, it's got to be a maximum. We call that the second derivative test for a maxima and minima. Let's examine concavity for this function. X cubed minus 3x. We want to figure out where it's concave up and where it's concave down. So if I see a problem and they're asking me about concavity, I know I have to find the second derivative. So our function is x cubed minus 3x. Y prime is 3x squared minus 3. And so y double prime is 6x. That sign chart will be pretty easy. This point of interest, now the places where the second derivative is 0, we don't call those critical values, but it is a value of interest, right? It's what we want to use on our horizontal axis. But we only have one value where it's 0. And it's negative if I plug in something negative, and it's positive if I plug in something positive. So we're using the sign chart to figure out where it's concave down and concave up, just like we use the first derivative sign chart to determine increasing and decreasing. So we know this is concave down when x is less than 0, and concave up when x is greater than 0. When we look at this sign chart, you know, we've determined where it's concave down and concave up. Kind of begs the question, like, is there anything interesting happening when the second derivative is actually 0? And places where the second derivative is 0 give us a possible inflection point. So, and you get an inflection point if the graph actually changes concavity. So here, the second derivative does change sign, right? It goes from negative to positive, so it changes from concave down to concave up, and that means that at x equals 0, we do have an inflection point. So I'm just going to recreate this. It's the same function, so I'm just rewriting what we did. So we said the second derivative is 6x, and then here's our sign chart. So the sign changes. At x equals 0, which means that we have an inflection point. And just like the maxima and minima, we need both coordinates. It's a point that we're finding. So when we plug in 0 to the original function, we'll get 0. So the point 0, 0 is an inflection point. And then down, you know, at the bottom of this page, we've just got a graph of this function. So we could see, kind of match this up. Here's on this side right here. This is concave down. On this side, it's concave up. And right here, that's our inflection point. That inflection point is pretty subtle, right? It doesn't really pop out. We know that there's got to be, the concavity changes somewhere. We could see definitely there's a concave up and a concave down. There's nothing drastic happening. Sometimes inflection points will appear maybe a little bit more recognizable. For example, like when I was talking about where you had a second derivative, where you had a critical value that wasn't a max or a min, and what that might look like. I said, maybe you have something that kind of flattens out and then keeps decreasing. There's an inflection, but that's a little bit more recognizable, right? We can see clearly that that goes from concave up to concave down, and we have like a recognizable change in behavior right in the middle there. Questions? Okay. So what we're going to do next, and we're actually going to get all the way through this, is we've been talking about how we use the derivatives to give us information about a function, right? Where is it increasing or decreasing? Do I have any max or min? Are there any inflection points? What's its concavity? Now we're going to try to put it all together to do a curve sketch. And on this page, I'm just sort of describing how we organize the information that we find, or at least how I like to organize it, because it helps me make a better sketch. So when I'm doing a curve sketch, the first thing I do is I just try to find any x or y intercepts. Like, that doesn't require calculus. If I set x equal to 0, I get the y-intercept. If I can find where the function itself is equal to 0, I get the x-intercepts. And I just do that because it gives me some points to kind of anchor the graph. Any fixed points I have kind of serve as anchors for the graph. Then I get all, I find my derivatives, my first and second derivatives, I make my sign charts, and then I organize all this information into a table. So as you make those sign charts for the first and second derivative, you get these sort of points of interest, the places that we actually mark down on the horizontal axis when we make a sign chart. So you gather up all those values. You use those to kind of partition or cut up the real number line. And then you put in, you list your intervals or your values. So like, let's say I have, one of my critical values is -2 or something. Then, and maybe that's my only critical value. I end up with an interval, say from -infinity to -2. Then I stop and see what's happening actually at -2. And then I go from -2 to my next value, I'll call it A or something. And then I stop and see what's going on at A, and then I make my next interval. Right, so we're kind of partitioning up the real numbers. I fill in this table. The only place where I fill in the f of x column is at these, when I stop and have an actual value. At the intervals, I don't do anything there. And when I actually plug in a value and get a y-coordinate, that'll be a point that serves as like an anchor for my graph. The first derivative and second derivative, all you're doing is it positive, negative, or 0 in all of these. So you're just keeping track of the sign. And then a conclusion. So for example, if on an interval I have the first derivative is positive and the second derivative is negative, my conclusion here would be increasing concave down. We're going to do an example, and this will take a little while, but it should give us a good idea of like how we kind of put all of this stuff together. Okay. So we're going to sketch this curve. So we're going to get our first and second derivative information. So let's start with the first derivative. I'm going to find y prime and the critical values. So if y is 2x cubed plus 3x squared minus 12x, we're using the first, we're using just the power rule. So we get 6x squared plus 6x minus 12. Now, if I'm going to make a sign chart, I want this to be factored. So I think the first thing I'll do is take out a 6. And then we can unfoil and get plus 2 minus 1. So there's our factors. What are our critical values?
-1.
Mm-hmm. Now, I know that I'm going to need the y coordinates eventually, so I'm just going to go ahead and find them. So I get 20 for the y coordinate, and then at x equals 2, and at 1, -7. Once you have your critical values and you have your first derivative in factored form, we can make a sign chart. I'm only listing the factors x plus 2 and x minus 1. You could include a row for the factor of 6, but 6 is always positive, so that's not going to affect the sign. And then a row for my derivative. X plus 2 is 0 at -2. It is negative to the left and positive to the right. X minus 1 is 0 at 1. It's negative to the left and positive to the right. And now we can fill in our bottom row. So for values less than -2, I've got a negative times a negative, so there's a positive. In the middle, that product is going to be negative, and at the end, it's all positives all around. And so I'm going to just leave that, right? So a lot of the time, or in previous examples, at this point we do some analysis, but I'm going to leave that. I'm going to put all of this information back into that sort of table that we talked about on the last page. This is just sort of information that I'm going to use to put in that table, and we'll draw some conclusions then. So we've got our first derivative stuff buttoned up. Let's get our second derivative stuff. Let's find y double prime, and then the possible inflection points, which I'm going to abbreviate as PIP. So our first derivative. Now so we have the first derivative written in a couple of different ways up there. I've got, here it is, here's the version that we used to make our sign chart. And here's the version before we factored it. You could start with either of those and take the derivative to get the second derivative. But if I want to do as little work as possible, which form am I going to pick?
Unfactored.
The unfactored one, right? Because I don't want to use the product rule. So y prime is 6x squared plus 6x minus 12. So that means our second derivative is 12x plus 6. Great. All right, so the second derivative is linear. We could take out a 6 if we want. Really, that's up to you. I don't know if it makes it any easier to work with, but it's just a linear function, so we can find where it's equal to 0 pretty easily. So the second derivative is 0 when 2x plus 1 equals 0. And that gives us negative a half. And I know that I'm going to need the y-coordinate as well eventually, so I'm going to just find it now. Six and a half. We can make our sign chart for the second derivative. There's, we don't need many rows. In fact, we can go just straight to the second derivative. It's 0 at negative a half, right? And then if I plug in something less than negative a half, let's say I plug in negative 10 to the second derivative, it's going to make it negative. And if I plug in something bigger than negative a half, if I plug in 0, it's going to make it positive. So we have gathered all of our information, all of our first derivative and second derivative information. Now we're going to be ready to make that table that we talked about in the last page. Our points of interest. So the values I'm going to use to kind of partition up the set of real numbers are the critical values and the spots where the second derivative is 0. So we've got 3 of them. And what I want to do, here I'll do this up here in between, just to kind of illustrate how, if this is a real number line, what I'm doing is I'm just marking down these values in the order in which they appear. So like here's negative 2, negative a half, and 1. So what I'm going to do is have an interval for all the values less than negative 2. I'm going to have a row for that interval. I'm going to have a row for this value. I'm going to have a row for the interval in between those two values. I'm going to have a row for that value. I'm going to have a row for the interval in between those two values. I'm going to have a row for this value. And then finally, a row for the interval going from 1 to infinity. So we're going to have 1, 2, 3, 4, 5, 6, 7 rows here. Right, so my first interval was from minus infinity to negative 2. Then we stop and see what's going on at negative 2. Our next interval was from minus 2 to negative a half. And we stop and see what's going on at negative a half. Then from minus 1/2 to positive 1. Stop and see what's going on at 1, and then from 1 to infinity. Does that part make sense, how we picked what rows we need? Okay. So now I just fill them out column by column. The y column, I'm only putting stuff in for the values that I actually found the y coordinates for. So at negative 2, we said y was equal to 20. At negative a half, we said at 1, we said it's negative 7. And at negative a half, we found that it was 6.5. So I'm done with that row. Those just give me anchors for my graph. y prime. So now, okay, we made the sign chart for y prime. All we want to do right now, I'm going to scroll up to this sign chart that we made for y prime. I'm going to take this, imagine taking that row, that bottom row, and like rotate it like 90 degrees and then just put it down that column. So I know it starts out positive. It's going to be 0 at -2 and 1. It starts out positive. It's negative in between those two. And then it's positive afterward. We're going to do the same thing for that sign chart that we made for the second derivative. Just take this row. Imagine that we're like rotating it, 90 degrees, and then just put it down the column. It is 0 at -1/2. It's negative ahead of that, and it's positive thereafter. We've got everything filled in now that we need in order to draw our conclusions. So this first row, y prime is positive, y double prime is negative. What do we conclude about what's going on with our graph?
Concave down.
Increasing concave down. Now, at -2, that was a critical value, right? So the first derivative is 0. What's going on right at that point? And how do we tell?
Inflection point.
Well, it's not an inflection point because we only get inflection points when the second derivative is 0. So let's skip that row first for now, and let's go to the next row, and then we'll come back to that one right after. The row for the interval from -2 to -1/2. What are our conclusions there? Decreasing concave down. Okay, now let's think about that other row right before it. We said that in the interval before, from -∞ to -2, it's increasing. And in the interval after, it's decreasing. What does that mean about what must be happening right at x equals -2? Can you say that louder? Well, like, did you say stays the same? I'm having a little bit of a hard time hearing because I think you're a bit far away from the mic, but...
Yeah.
So it's kind of levels off a little bit, right? It's not increasing or decreasing. What happens when a graph goes from increasing to decreasing?
Maximum.
It's a maximum. Okay, so we have a maximum at the point -220. There's two ways we can determine that we have a maximum there. By checking to see that the sign of y prime goes from positive to negative, right? So that it goes from increasing to decreasing. Also, note that the second derivative is negative there. So if your function is concave down at a critical value, that corresponds to a maximum. Those two different ways to determine whether or not you have a maximum or a minimum, the first derivative test and the second derivative test, will always be consistent with each other. If you've organized your information and you find that the first derivative test tells you it's a max and the second derivative test tells you it's a minimum, there's an error in your work somewhere. They'll always agree. Our next row is at x equals -1/2. What's happening there? It is not a minimum because the first derivative is not 0, so it can't be a max or a min. It's an inflection point. The second derivative is 0. I know because it's 0, I know it's a possible inflection point. Then the way I know it's an actual inflection point is that the second derivative changes sign. The next row, it's concave up. So this is an inflection point. What are our conclusions for the interval from -0.5 to 1? I heard the concave up part. What did you say first? Yeah. In our next row, what's going on when x is equal to 1?
Oh.
It's a minimum. Right, okay, so the first derivative is 0, so it's a critical value. We could have a max or a min. How did you determine it was a minimum and not a maximum? Yeah, it goes from decreasing to increasing. Also, that's consistent with the fact that it's concave up at that point. How about from 1 to infinity? What's going on at our last interval? Great. Okay. We've got all of our conclusions. Everything's organized nicely. Now we can get a sketch. Let's begin. So I gotta figure out what I want to do with my scale here, right? I don't need to go very far to the left or to the right on the x-axis, but I do need to go as high up as 20 on the y. So I think I'm going to use different scales for the x and the y-axis. So maybe like 1, 2, and then I'll go up by 2s here. Okay. The first thing we plot are our anchors, right? The actual points we know. So at -2, we're up here at 20. At -0.5, we're at 6.5. At 1, we're at -7. And then there's one other anchor we could get, which is if you look at the function itself, I could plug in 0 and just get the y coordinate. If you x equals 0, it gives you y equals 0, so I know it goes to the origin. And that's just an extra point that took me no work to get, so I may as well use it. So I've got these anchors. Now I'm just going to use our conclusions to figure out what's happening. At -220, this is a max, so it's got to do something like this, right? And heading into that max, right, when x is less than -2, it's increasing concave down. That's got to do something like that. Heading out of this max, it's concave down. We get to this inflection point. It heads into the min, and it's got to turn around there. And that inflection point is kind of subtle in that we don't see a drastic change in behavior there, but it is the actual point where it switches from concave down behavior to concave up. It turns around at the minimum, and then heading out, our last row says it's increasing concave up. How's that? What I like about this is that we could determine the whole behavior of a function. We didn't have to plot more than 1, 2, 3 points, and we plotted a fourth because it was easy to get. But we only actually found outputs for 3 points, and then we're able to use the derivatives to figure out the behaviors in between those points. So as you're doing this, sometimes curve sketching can be frustrating just because they're big problems, right? We just did a lot of work to get the graph of this. But just keep in mind that what we're doing, we're using curve sketching as a proxy to help us understand the full behavior of a function on its domain, which is a valuable skill. So you guys don't have school tomorrow, right? We're having a quiz on Tuesday. That quiz on Tuesday is going to cover these applications. So maybe tangent, normal line. Again, there's only going to, I haven't written it yet. There'll be 4 problems, you know, as usual, that'll come from these topics. There will absolutely be a related rates problem. And then there will be a question about curve sketching, but it won't be a full curve sketching problem because those take too long. But what I might do is say, here's a function, tell me where it's increasing or decreasing, or tell me where it's concave up or concave down, or can you tell me where it has a max or a min? Like, give you a question to answer that'll require you to use either the first or second derivative and maybe make a sign chart for it. So those are the types of the type of question that you might get on a curve sketching problem. Are there questions on any of the examples that we did today, or what to expect on Tuesday? Okay. I think what I'll do then, there isn't any more new material that I wanted to get through today. So if it will be helpful, I'll just go ahead and let you use the rest of your class time to work on the practice exercises, and I'll see you all again for class on Monday. Does that sound okay? All right. Thanks, everybody.